See you guys again in a new topic. So today we're going to talk about boiling point of a liquid. Alright. So boiling point of a liquid. Under this one, I'm going to talk as well about vapor pressure. Okay. So we are going to talk about evaporation process. Okay. So evaporation process is a process of transition between liquid molecules to gas molecules. Okay, for your information, this process is a spontaneous reaction where it can happen at any temperature. Okay, but the amount of molecules, liquid molecules that being converted into gas molecules, or we can call it as vapor, depending on the temperature of the surrounding. Okay, so basically it's a slow process, but if you are applying certain amount of heat, so this reaction might be occurring at a higher speed. Okay, so for a molecule to evaporate, it must follow up certain criteria, which is the first one. This evaporation process only takes place with the molecule which is located close to the surface. Okay, as you can see in this picture, okay, we have a beaker with a water molecule. Okay, so this one in this water surface. Okay, so we have here water molecule. Okay, so the molecule that is located close to the surface can evaporate, converting themselves into a gas molecules. Okay, so from liquid to gas. Okay, provided all of these molecules have enough energy to overcome the intermolecular forces that hold the liquid molecule together. Okay, so we already talked about intermolecular forces in chapter 4, which we have hydrogen bond. Okay, secondly, under van der Waals forces. Okay, we have dipole forces. Okay, dipole forces is polar molecule. And another one we have London forces, which London forces is for non-polar molecule. So these three types of forces are known as intermolecular forces. Okay, so for these molecules to be converted into this gas phase, or sometimes we refer it as vapor. Okay, so this molecule must have these two criteria. Okay, so move on. Okay, so what is the importance of understanding the concept of evaporation? Because it relates to the concept of vapor pressure. Okay, so what is vapor pressure? So the hint there is vapor and pressure. Okay, so if we have an open container system, okay, so the liquid molecules here, okay, which is close to the surface and have enough kinetic energy to overcome the intermolecular forces, will be transformed, okay, from a liquid to a gas molecule. Okay, so this molecule over here are all gaseous molecules. Okay, so gaseous molecule. Okay, sometimes we use it named as vapor. Okay, so this vapor, since this is an open container, so this vapor will escape. Okay, so gas or vapor molecule escape from the system or container. Okay, but if we are having a closed container, okay, so the liquid molecules, okay, so these are the liquid molecule, okay, which have enough kinetic energy to overcome the intermolecular forces and is located in close enough to the surface, so it get changed to gas. Okay, and this gas molecule cannot escape from the container. Why? Because we are having a closed container system. Okay, so what happened then? Okay, when we have having a closed container system, so this vapor molecule or this gas molecule will collide with each other. Okay, so gas molecule will collide with each other. Okay, why? Because the gas molecule is trapped in the closed container. Okay, so the gas molecule trapped in the closed container, resulting in the gas molecule collide with each other. So when the gas molecule collide with each other, and then it also will collide with the glass wall or the container wall, which results in the formation of vapor pressure. Okay, so in this closed system, gas molecules collide with the wall of the container, resulting in formation of vapor pressure. Okay, so the larger the amount of vapor molecules present in that closed container, so the higher the vapor pressure in the container will be. Okay, so here, so the amount of vapor molecule present in the container will determine the liquid vapor pressure. Okay, so move on to the next page. Okay, so vapor pressure can be interchangeable by the effect of temperature. Okay, so again, as a recap, so this is a closed container system. So we have here liquid molecule. Okay, some of this liquid molecule will change into gas molecule. Okay, so this gas molecule will hit the wall, and since it hit the walls, it will give rises to vapor pressure. Okay, gas molecule hit the walls of the container. Okay, resulting in formation of vapor pressure. So, how to increase? Okay, so in order to increase the vapor pressure, we need to increase number of vapor molecules present. Okay, since the process of formation of vapor depending on two criteria, which is first, it must be located close to the surface. Secondly, the liquid molecules must have enough kinetic energy to overcome the intermolecular forces. Okay, so to increase the number of vapor molecule present means we can increase by applying heat or increase the temperature of the system. So more liquid molecules will have enough kinetic energy to overcome the intermolecular forces that hold them together. Okay, so this one is the Maxwell-Boltzmann distribution curve, which you will see more in chapter 6 later on, okay, under the topic of dynamic equilibrium. So there are two curve lines, which is for T1 and T2. So the blue line is for T1 and red line is for T2. Okay, so T1 shows that the maximum amount of molecule occupied at this level, which is amount of energy. Okay, so this one, the peak shows the maximum number of molecules. So average molecules is having this amount of energy. As you can see, okay, E1 and E2, at the higher temperature, which is T2, more molecules are having larger amount of energy. So E2 is greater than E1. Okay, so means increasing temperature will increase the kinetic energy of the molecule, and there is a specific amount of heat, amount of energy that the molecules need to have, and that one we name is activation energy. Activation energy will be talked or discussed further in semester 2. Okay, just to let you know, this activation energy is the amount of energy required for the molecules to break that intermolecular forces between them so they can get free and become a vapor. So it's being represented as this barrier E. Okay, so the area under the graph shows the amount of molecule having enough energy to break the intermolecular forces. Okay, so as you can see, under the blue line is smaller shades of area, but at higher temperature with the red line, we have a larger area of molecules having enough kinetic energy to break the intermolecular forces and converting themselves from liquid molecules to gas molecules. Okay, so this is the effect of temperature. So increase temperature by how we're going to increase the temperature? By heating. Okay, so increase temperature will increase kinetic energy of the molecules. So increase number of liquid molecules have enough kinetic energy to overcome the intermolecular forces. So increase number of gas molecule or vapor. So what happens then? More vapor means more collision with the walls of the container, so resulting in higher vapor pressure. Okay, so vapor pressure is largely related to the volatility of the molecule. Okay, as you enter the lab, some of the reagents we classified it as volatile liquid. Some of the reagents are classified as non-volatile liquid. So volatility means how easy for the liquid molecule to be converted themselves into a vapor gas or vapor molecules or gas molecule. So high volatility means it's very easy for the liquid molecule to be converted to gas. Low volatility means it takes longer time to transform from liquid into gas or vapor molecule. So in the lab, we always classify the liquid as volatile liquid or non-volatile liquid. And I already talked to you during our lab session. Any volatile liquid, if you need to carry out the experiment using volatile liquid, so they're going to keep it in the fume hood. But non-volatile liquid, normally we can just place it in on our bench. Okay, so the most volatile liquid that we can find out in our daily life is in a perfume. So this is my favorite perfume, Verawang Princess. Okay, so perfume is one of the example of volatile liquid. Even though it's volatile, but it's still not that harmful, because volatile liquid for perfume means the liquid molecules in your perfume can easily vaporize into gas. So from the gas molecule is what you get the smell of the perfume. Okay, if the liquid molecule in the perfume does not transform into gas molecule, you cannot detect what kind of smell is present. Okay, so this is it. So once we remove the cap, okay, so this liquid molecule, okay, inside the liquid, inside the bottle, okay, if it's close to the surface and it have enough kinetic, okay, again, close to the surface. So first, secondly, enough Ke to overcome the IMF. So the liquid molecule can change themselves into gas molecule or vapor molecule. So when we remove the cap, okay, so we remove the cap, this gas molecule will escape from the bottle and we smell the good smell of the Verawang Princess perfume. Any kind of perfume will have that same chemistry pattern. Okay, all right. So what is important for you to understand about the concept of vapor pressure? Because it's related to boiling. Okay, so evaporation, just now we said that it's a spontaneous reaction. Evaporation, okay, spontaneous, but it's a slow process. Okay, which liquid to gas as well. Okay, so another process which convert liquid molecule to gas is boiling process. But this boiling process, okay, does not involve liquid molecule that is close to the surface. Okay, because evaporation only takes place for the liquid molecule that is close to the surface. But for boiling, it will involve all the molecules in the container. All molecules in the entire molecule. Sorry for the typo, it should be in the entire container. Okay, so all the liquid molecules need to change from liquid to gas. So in order for that to happen, okay, so that means all the liquid molecules must have enough kinetic energy to overcome the intermolecular forces that hold the liquid molecules together. Okay, so this boiling process will only take place at certain temperature, which is known as boiling point, and each liquid, each reagents, each compound have specific value of its boiling point. Okay, for example, water, it will boil at 100 degrees Celsius. Okay, so this boiling point will occur when the vapor pressure of the liquid is equivalent to the atmospheric pressure. Okay, previously we already learned about vapor pressure from a few previous slides. So again, let's recap. Vapor pressure is the result of liquid molecules change to gas known as vapor. So this vapor molecule which is present in a closed container. Okay, so closed container. So we have liquid here. Okay, which some of it might be released as vapor through evaporation process. Okay, through evaporation process. So this gas molecule will hit the wall and resulting in vapor pressure. Okay, so if it's a volatile liquid, easily to evaporate, so high vapor pressure. Okay, so if it's non-volatile liquid, hard to evaporate, so low vapor pressure. Okay, so since boiling point will happen when vapor pressure of the liquid is equivalent to atmospheric pressure. Okay, how are we going to increase the vapor pressure to be equal to the atmospheric pressure? By applying heat. Okay, so for those volatile liquid which already have high vapor pressure, so it just need a little amount of energy to raise its vapor pressure to equivalent to the atmospheric pressure. But for the case of non-volatile liquid, okay, which have low vapor pressure, so it will require a lot amount of heat, okay, for its vapor pressure to reach the atmospheric pressure. So what is the value of atmospheric pressure? The standard one at room temperature is 1 atm, or you can convert it into other units, which is millimeter mercury or torr. Okay. Okay, so therefore, boiling point or boiling process will related to the initial vapor pressure of the liquid at room temperature. So, volatile, high vapor pressure. Okay, and non-volatile, low vapor pressure. Okay, so these are the whatever that I talked about just now. You can read it in this simple explanation. Volatile liquid can easily evaporate to form vapor molecule or gas, okay, which results in the initial high vapor pressure of the liquid. In order for the liquid to reach its boiling point, the liquid only needs little amount of energy for all the liquid molecules to evaporate and raise its vapor pressure to be equivalent to the atmospheric pressure. Thus, volatile liquid will have low boiling point. Okay, let me give you an example. Okay, let's say we have molecule A, which is a volatile liquid. So, it can easily evaporate and change itself from liquid molecule to vapor molecule at room temperature. A spontaneous reaction. Okay, let's say it have 0.7 atm of vapor pressure. And for boiling to happen, it must equal to 1 atm, which is your atmospheric pressure. Okay. So to reach from 0.7 to 1 atm, we need to add another 0.3 atm. So heat supply is to get this 0.7 plus 0.3 to 1 atm. So this is just a small amount of pressure changes is needed. So small amount of energy is required. Okay, let's look at this vapor pressure curve. So mostly everything will be shown in the vapor pressure curve. Okay, so we have three different molecules here: diethyl ether, ethyl alcohol, and water. Okay, so at room temperature, which is here, this is 25 degrees Celsius. Okay, look at the vapor pressure for each one. Okay, so red line, where this red curve intersects this 25 degrees Celsius. Okay, so this is the vapor pressure for diethyl ether. Okay, this is vapor pressure. So this one for ethyl alcohol is here. So this is vapor pressure of ethyl alcohol. Okay, and this one is the vapor pressure for water. Okay, what you can say is, okay, diethyl ether has the highest vapor pressure. Highest vapor pressure means this has high volatility. Okay, followed by ethyl alcohol and water. Why do you think so? Okay, because in water it's held together by hydrogen bond. Okay, hydrogen bond is the strongest intermolecular forces. Okay, ethyl alcohol as well as is also have hydrogen bond. Okay, hydrogen bond in the molecule. Okay, the difference between these two is water have 2 hydrogen bond per molecule. Ethyl alcohol only have 1 hydrogen bond. So water has stronger intermolecular forces compared to ethyl alcohol. Whereas in diethyl ether, we only have the weak London forces. Okay, so the weakest intermolecular forces in diethyl ether make it easily to evaporate, changing itself from liquid to vapor molecule at the room temperature. Okay, so diethyl ether is the most volatile compound in this example, which means it can evaporate easily to form gas or vapor molecules at room temperature. Okay, so this shows that diethyl ether has the weakest intermolecular forces between its molecule. Therefore, okay, it already have about here, okay, at 25 degrees Celsius, you already have about this much amount of pressure. It's 750, for example. Okay, so for it to reach the atmospheric pressure, okay, to reach boiling point, it just need another 10 millimeter mercury to be equivalent to 760 millimeter mercury. Since the change in pressure needed is just this small amount, so the amount of heat needed is very small, so that's why it has a very low boiling point. Okay. In comparison with water molecule, so its vapor pressure at room temperature, I think is just about 20 or 10 millimeter mercury. Okay, so about 10 millimeter mercury. Okay, so for it to reach its boiling point, you need to raise its vapor pressure from 10 into 760 millimeter mercury. So this 760, so how much increment is needed? About 750 millimeter mercury. So that means a very large amount of energy is needed to raise the pressure from 10 to 760. That's why water has very high boiling point, and in this example, highest boiling point. Okay, so let's give another example between methane, water, and chloromethane. So all of these are 4 electron group compound. Okay, but in the methane, okay, it's a non-polar molecule, so it have London forces. In the water molecule, it's a polar, and it have the presence of hydrogen bond. Whereas in chloromethane, it's polar molecule, okay, but it will have dipole-dipole forces. If you rank in the terms of strength of intermolecular forces, hydrogen bond is the strongest. Okay. Secondly is dipole-dipole forces, and London forces is the weakest, the third one. Okay, so we can predict that methane will be having the highest vapor pressure. Highest, followed by chloromethane, and lastly water. Okay, so vapor pressure. Okay, so methane highest, followed by chloromethane and water. So we can expect, okay, the boiling point to increase in the same order, which is methane has the lowest boiling point, okay, and then chloromethane and water. So this one increasing boiling point. Okay, so just for you, in easier for you to remember this, vapor pressure is inversely proportional to boiling point. If it's already have high vapor pressure, so that means it will have low boiling point, because you just need a little amount of energy to raise the original vapor pressure up to the atmospheric pressure. Okay, which this vapor pressure is related to the strength of intermolecular forces. If the molecules have strong intermolecular forces between them, so you will require more energy. More energy means less molecule will evaporate, changing from liquid to gas, resulting in low vapor pressure. Okay, so when it's become low vapor pressure, means you need to raise that vapor pressure to be equivalent to the atmospheric pressure. You will need a large increase in vapor pressure. Thus, more energy is needed. That's high boiling point. Okay, so your boiling point of any molecules will be determined depending on two different factors, which is the first one, strength of IMF. Okay, so if it has a strong intermolecular forces between them, so means strong IMF, low vapor pressure. Strong IMF mean low vapor pressure. Okay, so high boiling point. Okay, secondly, it is the atmospheric pressure. Okay, so the value of atmospheric pressure is a fixed value, but it depends on the altitude or the location of that place. For example, in the Mount Fuji, with this height, at the top of Mount Fuji, okay, so it will have different value of atmospheric pressure compared to the Mount Everest. Okay, so on the Mount Fuji, okay, water has higher boiling point compared to the Mount Everest, which has higher tops. Okay, that means atmospheric pressure at the higher tops is lower than the one with at the Mount Fuji, which has lower altitude. Okay, so again, at different altitude, you will have different atmospheric pressure, and atmospheric pressure is a fixed value, so you need to find out. Okay, the normal atmospheric pressure is at 25 degrees Celsius and it's 1 atm. Okay, so again, then boiling point depends on the strength of thermal forces, which relate to the vapor pressure, and secondly depends on the atmospheric. Okay guys, so this is the summary about the factors that will affect the boiling point of your liquid. Okay, so the first one is the intermolecular forces. Okay, where it states that the stronger the intermolecular forces, the greater amount of energy is needed to overcome the intermolecular forces. Therefore, it is harder for the molecule to evaporate, to turn into gas vapor molecule. Thus, the molecule will have low vapor pressure, and this will cause a larger amount of energy is needed to reach the atmospheric pressure value. As a result, it will have high boiling point. Okay, so for the strength of intermolecular forces, again, I emphasize to you, refer to your notes on chapter 4. We have 3 intermolecular forces. which is hydrogen bond, London forces, as well as dipole-dipole forces. Okay, and secondly is atmospheric pressure, which atmospheric pressure depends highly on the altitude. So the higher the altitude or the greater the altitude, the smaller the value of atmospheric pressure. Therefore, a smaller amount of energy is needed to raise its initial vapor pressure to reach the current atmospheric pressure, which will result in a lower boiling point at higher altitude. Alright guys, so it's all for today. Thank you for watching.